In summary, to convert a decimal fraction to IEEE internal binary storage, step by step, we need to fill in the sign, the exponent, and mantissa. And from left to right, binary digits of mantissa represent these two base fractions. If the resulting binary fraction can be fully assembled from a sum of these two base fractions, this is called a dyadic fraction. So we can take a look at another example, 3.14. This is my decimal fraction. Obviously the sign is 0 because the number is positive. Then we take the integral part, convert it to a binary number, which is 11, and write it here. Next, we take the decimal fractional part and multiply it by 2, and then we write it down just below the first mantissa bit. So this will be 0.28. Next, we take the fractional part again and multiply it by 2 and write down the result, aligning it with the next bit in mantissa positions. Then again we multiply the fractional part by 2 and write it right next, and we just keep going, but remember only the fraction part needs to be multiplied by 2 when moving to the next bit. So here we have 0.24 and so on. I can just copy and paste it from this example we have. Just write it down. And then the next number is 0.88, but I'll stop right here because we already accumulated enough precision over here to be close to this initial value. And this is our binary fraction, 11.001000111, and so forth. So what I'll do next, I'll push this number down here and just project these values. So 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1. And for now, just fill it in with zeros because I'm pretty sure it's close enough to this value. In summary, the integral parts of these fractions are mantissa bits, and we're completely done here. And this was the difficult part. Now comes the easy step. We normalize the fraction by shifting the radix point to the left. In our case, it's going to be to the left, or to the right, to make sure that the integral part is just binary 1. And so this denormalized binary fraction, I'll just write it down here one more time. So it becomes this. So now it's normalized, but we must now remember to add the exponent, which is to multiply the normalized binary fraction by 2 raised to power e, like this. So e equals the number of radix steps, this radix shift steps. In our case, it's just 1 because it shifted from right to left, and it's a positive 1. So this is 2 raised to the first power, so it's just 2. And this fraction multiplied by 2. And now I would like to align this fraction and actually cut off this 0 because this is now our mantissa right here. So we're ready to fill it in. Okay, so this is our mantissa. And now we're ready to fill in the exponent. Of course, the exponent is always stored as 127 plus this value. All right, so 127 plus this value. That's what we have to store. So it's 128. So basically we convert 128 to a binary number, and it's just this, right? So we're now ready to fill in this. Okay, and this is 0. So we can now try to verify how close we are to this initial value by using the floating point converter online. So we can just simply paste our binary result right here, get rid of these spaces, okay, and just hit enter. And so you can see that this is 3.1398 and so forth, so it's very, very close to this. Obviously, we just chopped off the precision here and just left it at this level of precision right here. The rest we just kind of ignored. So this worked well, and I'm all done with this example.